So I said that I was going to do this problem as part of the other video, but that video actually got to be fairly long, so I broke it out into its own short piece. But we're using the Arrhenius equation to try to determine what the activation energy would be for this particular reaction of nitrogen dioxide and carbon monoxide. And this is a two-point Arrhenius equation problem. What I mean by that is we have two different temperatures where the rate constant has been measured, and we're going to use those two along with the two-point Arrhenius equation to determine what the activation energy would be. Better way would be if we could measure the rate constant at a series of 3, 4, 5, 6 different temperatures, and then use the full-on Arrhenius equation, fit the natural log versus 1 over the temperature to get a straight line and measure the slope and intercept of that line, and from that we could get the frequency coefficient A, and we could also get the activation energy. But we're going to do it with the two-point version because that's the one that's going to be easiest for us to simulate in a class like this. Okay, so the equation that we're going to use, the two-point Arrhenius equation, is log of rate constant 2 over rate constant 1 is equal to the activation energy over the gas constant times 1 over first temperature and 1 over minus 1 over the second temperature. So, you know, there have been other times where we have done calculations where we've had to say, okay, which temperature is which. For this one, I would say probably the easiest way to set this would say the lowest temperature is going to be T1, and that would make the rate constant that goes along with it small k1, and then the larger temperature would be T2, and the larger rate constant would be K2. You know, so now we have the values for all those different variables. You can probably see that this is going to become very much a plug and chug type problem. The only thing to, the only piece of the puzzle that we don't have down here is the rate constant, and R equals 8.314 joule per mole Kelvin. And that gas constant is going to determine what the unit of activation energy would be. It's going to end up being joule per mole. So now we can just go through and plug everything into the expression, and we have natural log of the rate constant 2, which would be 567. That's a fast reaction. Over the rate constant 1, 2.57. The activation energy is what we're trying to determine. And you might say, okay, you didn't put any unit in here. Because these are a ratio, one over the other, they both have the same unit, inverse molar, inverse second. And so those units are going to cross out, so I didn't even put them into the problem here. The others I'm going to put in just so that we can follow them along and make sure that we've done the calculation in the correct manner. R is 8.314 joule per mole Kelvin. Our temperatures are in Kelvin. T1 is 701 K, and T2 is 895 Kelvin. And it turns out that the Kelvin here and the Kelvin here will cross out, and they're going to leave us with the unit of joule per mole. We'll see that'll be useful for us here in a second. So we go through and calculate this ratio. We get the natural log of 220.62 equals activation energy over 8.314 joule per mole. In the parenthesis, if we do 1 over 701, we get 1.4265 times 10 to the minus third minus 1.1173 times 10 to the minus third. Take the natural log of 220, and you end up with 5.3964. Again, taking more digits so that I don't have rounding errors. All right, is equal to the activation energy over 8.314 joule per mole times, I'd subtract those two and I get 3.0918 times 10 to the minus fourth power. And what I'm going to do next is I'm going to divide both sides by 3.0918 times 10 to the minus fourth, and then multiply both sides by 8.314. Alternatively, you might look at this and say, well, I can divide 8.314 into 3.0918. That's a perfectly fine way to do it as well. Either way, the algebra of this leads us to an activation energy. And if you're looking at that saying, I'm not sure how you did the algebra, let me know. I'll gladly find a time to meet with you and show you how to work through something like that. You should end up with 1.45 times 10 to the fifth joules per mole. And then if you convert that to kilojoules per mole, just simply because the problem is asking for the activation energy in kilojoules per mole, you'll end up with 145 kilojoules per mole. So that's Arrhenius equation. That's how we would plug everything into the two-point Arrhenius equation, the one that doesn't involve us graphing things. Yeah, there's not a whole lot more than that. Hope you have a great day.